Okay, so we're back in business. Before I get started, are there any questions about what we've done or what we might do or about the assignments? No, okay. So shouldn't take this too seriously, but I'm going to talk about graph products, which is something we can do easily using the chronic product, and then homomorphisms and automorphisms. I don't think I'll get through everything on this list today. So a graph product, well, you're free to define whatever products you want, but for the context I'm dealing with, a graph product, the product of x and y will have vertex set the Cartesian product of vx and vy. So the vertices are the product of the order pairs vertices x comma vertices of y. Okay, so that tells you what the vertex set is, but to complete the definition, of course, I've got to tell you what the adjacency rule is. And there are a number of cases. In fact, there's an old paper by Emmerich and Isbicki that works out the claims in a certain sense. There are only 17 different graph products, but we're not going to go anything like that. So the two that we use are the direct product and the Cartesian product. And so, but let's get to those. So the direct product of x and y is a graph with the vertex Cartesian product, as stated, and two pairs are adjacent if and only if the first coordinate's adjacent and the second coordinate's adjacent. Okay, I'll give you a picture in a minute. The point I wanted, a little bit sloppy here. I mean, in this case, you're saying that these vertices are adjacent in the product if and only if they're adjacent in x and these are adjacent in y. So that tilde is carrying a bit of a load there, but it's, and so I'll often put subscripts, but something under the tilde to indicate what. So when you've got more than one graph in sight and you say two things are adjacent, it needs to be clear adjacent in which graph. Okay, so that's the direct product. Now I just picked one very simple example. I took the direct product of P3 with itself. So if we have P3 having vertices, say 0, 1, and 2, then this would be 0, 0, 0, 1, 0, 2, and this would be 2, 2, and this would be 1, 1. And those. So they're the order pairs. Now, a couple of things about this. The direct product is in, well, the jargon is it's the categorical product for graphs, but we won't go into that. But, so it's a natural product. It's somewhat less important and it's somewhat nastier than the next product we're dealing with. The thing to notice is that basically if the point here is that that's 0, 0. So 0 is adjacent to 1 in the second copy of P3, and 0 is adjacent to 1 in the first copy of P3. So each edge, if you have an edge in the top graph and an edge in the bottom graph, then what you see you see 4 vertices, and those 4 vertices are joined by a cross. So in general, you have a graph G on top or graph X on top, a graph Y there. And whenever there's an edge in X and an edge in Y, you put in a cross. Okay, and that's one reason why we generally use the cross for the, or it is the reason why we use the cross for this product. So this is the direct product. And the easiest way to define this is actually using the adjacency matrices. The dilemma is that the adjacency matrix for the direct product is just the chronicle product of the adjacency matrices of the factors. And that's a perfectly good definition. Now, the other thing about this picture is that although P3 is connected, the product of P3 itself is not connected. And so this is a sort of a nasty property of the direct product, that you can have connected graphs as inputs and get something which is not connected as output, which is something you don't like. There's also an issue with the products. You often want to sort of say that if x comma y1 is isomorphic to x comma y2, then y1 is isomorphic to y2. So you want to cancel. Well, you can't with the direct product. So anyway, it's there, and we'll see it coming up from time to time. Now, more importantly for us is what's called the Cartesian product. Okay, same vertex as before, and order pairs are adjacent if either the first coordinates are equal and the second coordinates are adjacent, or vice versa. So in this case, the rough picture is you take let's say if I take copies of X and then I put copies of Y in the columns. Okay, now the picture here is that if I have an edge in the top graph and an edge in the side graph here, then those 4 vertices will give me a square. And so that's one reason why we write it as P3 squared P3. Okay, so we use square for the Cartesian product. So the notation serves as a reminder of what you do. Now the Cartesian product will play a role because of the important thing. Well, part of it works. It's going to come up in when we start talking about the physics, because if we have a composite system, then it's given by a Kronecker product. It's given by a tensor product. But if we're looking at a walks on a graph and we get a composite system, the product we need will turn out to be the Cartesian product. So the direct product comes up from time to time, but the Cartesian product corresponds to something which is physically natural. So in other words, the composition of 2 quantum systems based on graphs will correspond to the quantum system on the Cartesian product of the 2 graphs. So that's one reason. And again, you will see that coming. Now, the formula for the adjacency matrix of Cartesian product is given by this. And I'm going to put that down in the exercises. Now, so it's a sum of 2 terms. Now, the thing to notice is that those 2 terms commute, because you multiply AX by I and I by AY. So those 2 terms commute. So the exponential of the adjacency matrix of this is the product of the Kronecker product of the exponentials of the 2 factors. Now, we've got to be a bit careful here because, and you should think about this. I don't think it's worth making an exercise, but there's a line of reasoning hiding in there, hiding in here. Where are we? So what is X of AX tensor I? I claim it's going to be X of AX tensor the identity, and similarly this will be the identity tensor X of AY, and then when you multiply them, the identities get absorbed and you get this. So there's actually a step going on here, but it's easily filled in, and I'm going to leave you the pleasure of solving that if you're worried. So the as I said, so the composition of some of the systems we're looking at based on graphs will be a physical system based on the Cartesian product of the input graphs. And so the Cartesian product is quite important from that point of view. Now, as I said, there were, well, according to Emmerich and his sheet, there were 17 products. I'm just going to give one more by way of example, which might come up. It's called the strong product. And the rule for the adjacent, and in some sense, or the adjacency matrix that is the sum of the adjacency matrix for the direct product and the adjacency matrix for the Cartesian product. And so that's what I've written down here. And in this case, I didn't bother drawing an example because I'm not sure I'll need it. But in this case, if you have an edge in the left-hand graph and an edge in the top graph, then you'll get a little square with diagonals. It'll complete graph on 4 vertices hiding in there. This comes up in the work on Shannon capacity and the work that Lovis did. The strong product is natural there. But for our purposes, the Cartesian product will be the main one. And we'll have a bit play a bit with the direct product occasionally, perhaps. There's all this stuff is in the my book with Royal. There's nothing well, but this one I won't have anything about exponentials, but the products are there, at least the Cartesian product and the direct product. Any questions at this point? Okay, so so now I want to start talking about homomorphisms, automorphisms. Now, there's various reasons for this. One is that we can use automorphism groups to help construct interesting graphs that we want to work with, or have graphs that are interesting, and we can use automorphisms to get information. The other thing is that later in the course, we'll be talking about quantum analogs of the homomorphisms and automorphisms. And it makes more sense to look at the classical versions first before we look at the quantum versions. And again, the material about homomorphisms is in the Algebraic graph theory book. And stuff about the automorphisms. So, okay, I have to start with definition. So I've got a map from the vertices of graph X to the vertices of Y. It's a homomorphism if the images of two vertices are adjacent whenever they're adjacent in X. So if, in other words, if U and V are adjacent in X, then the homomorphism has to map U and V to adjacent vertices in Y. Now, the thing to bear in mind here is we're working with simple graphs with no loops, and so no vertex is adjacent to itself. So consequence of this definition of a homomorphism is you can't map two adjacent vertices to the same place, because equal vertices are not adjacent. Okay, now this is a convention, but it's a fairly standard convention. And if you really want to have, if you add loops, you can have more things, but we're working with simple graphs, no loops. And so it's important to realize that you can't map a pair of adjacent vertices to a single vertex. And a consequence of this is that the set of vertices in X, which map to a given vertex in Y, no two of those can be adjacent. I'll come back to that later on. So what are examples of homomorphisms of this? Two simple examples. One is if X is a subgraph of Y, then you have an inclusion map that maps the vertices of X to the vertices of Y, and that map is a homomorphism. Okay, now that's trivial, but it's there, and it plays a role from time to time. A second definition, which is more interesting, is that a graph is M-colorable. You can color the vertices with M colors, so adjacent vertices get different colors. If and only if there's a homomorphism from a graph X to the complete graph, that should be Kn. I can fix that, can't I? So coloring, so you can view the questions about homomorphisms as generalizations of questions about colorings. Now, this is a warning to be careful, because questions about coloring is already NP hard. And so in a situation, we're saying, well, we'd like to know more about homomorphisms, so we're going to study a harder, we'd like to know more about colorings. So let's start by studying a harder problem. But anyway, that's what it is. So that's a well-defined class of examples, and certainly provides motivation. I'm going to, for the immediate purposes, I can say that an automorphism is just an invertible homomorphism. This is not really the best definition to work with. I'll give it a better one before too long. But so an automorphism graph, which we're going to talk about, is a special case of a homomorphism. Okay. Now, the automorphism graphs form a group, the automorphism group, which we'll come to. The homomorphisms form a monoid. So the composition, the composition of two homomorphisms, so you have homomorphism X to Y and Y to Z. There's a composite homomorphism from X to Z, and the composition is associative. This is simply because composition of functions is associative. Okay, and homomorphisms of functions. Now we need to be careful when you come to the quantum situation. Homomorphisms will no longer be functions, but for the moment, that's in the future. So homomorphisms of functions, composition of functions, associative. And so if you have a set with an associative operation, you've got a semigroup, and we also have an identity, so that makes it a monoid. Okay, so I mean, it plays no real role because we have no list of monoids to work with or anything, but that's what it is algebraically. And now we come up to this term core, which has got two closely related meanings. We'll be careful here. So a graph is, say a graph is a core if whole homomorphisms to itself are automorphisms. And okay, so the examples. So any complete graph is a core. Okay, you can't if you have a complete graph. Where am I? Let's look at, say, K5. Terrible drawing. Yeah. The point is that I can't map any two vertices are adjacent, so they must get mapped to distinct vertices. And so the complete graph is a core. The slightly more interesting case is the odd cycles are cores. Because any proper subgraph of an odd cycle is bipartite. So one way of arguing this is in terms of colorings. This is a 3-color graph, but any proper subgraph, if you delete an edge or a vertex, the graph you get is bipartite, it can be 2-colored. And so from you could deduce from that. Another way of seeing it is maybe homomorphisms aren't hard to find, I should say. So in this case, if I identify these 2 vertices, so I squash these 2 vertices together, and I'll get it like this. Now, that's a homomorphism. So the point of this is that if you can find 2 vertices of distance 2 in a graph, you can construct a homomorphism to a smaller graph. So homomorphisms aren't hard to find. Now, if I forced you to look for automorphisms, you would decide that automorphisms can be hard to find, but finding some homomorphisms is never a problem. Okay, okay, fine. So the complete graph is a core. Any homomorphism to itself is an automorphism. Okay, so the endomorphism monoid is a group. Similarly, any odd cycle is a core. Okay, even cycles are bipartite. And so the core of a bipartite graph is always just a core of a bipartite graph with an edge is an edge. Okay, so I'm teaching here. So what about Peterson graphs? This is sort of one of the standardized graphs. Now I'm going to leave you to think about that one at this point. But so if you do think about it, you realize that it'd be nice to have a bit more theory before you try to settle the question. I think Gordon Royal has some programs for computing homomorphisms between graphs, but generally speaking, there isn't any. And so even the computer doesn't help you a whole lot. Now, there are theorems in the Algebraic graph theory book which give you the answer, but I'm just giving you sort of something to think about. So, when it first comes to you, it's not clear whether the Peterson graph is a core or not. Any questions at this point?
Yeah, I have a quick question about our definition of automorphism. I know you said that we'll have a different definition, but the definition that I'm used to, we need an automorphism to be from a graph to itself, right? Like an endomorphism.
Yes, you're right. Yes. Okay, so I can cheat.
And then I guess a second question is, we're just saying invertible homomorphism here. I know that in general, if you have a bijective graph homomorphism, that's not necessarily an isomorphism. Is that true when you restrict to endomorphisms? Like the inverse may not be a homomorphism itself.
I would. I think what I'm going to do is I'm going to say it's a very good question. I'm going to let you think about it. So if you have a bijection from the vertices graph to itself, so long as we deal with finite graphs, that will be an automorphism.
Okay, so that happens automatically.
Yeah, but I think, in fact, if you think about it, you should be able to see the reasons. Now, if you do think about it for a bit and you can't see the reasons, then ask me again.
Okay, thank you.
But it's probably something I need to write. Sorry, it needs some writing. I don't think a verbal explanation will quite get there. But I think if you think about it, it's straightforward. It is you got to be a little careful. Maybe I should have just said that automorphism is a homomorphism, left it at that. And there's probably no point giving us that definition of automorphism anyway. I said there was the term core is used in 2 slightly different ways. So we say a graph is a core if every endomorphism is an automorphism. That's definition number 1. Number 2, the second possibility is we have a graph X and a subgraph Y, and there's a homomorphism from X to Y, but there's no homomorphism from X to a subgraph of Y. Now, in that case, we say Y is a core of X. So the core of a graph is the smallest subgraph that it has a homomorphism to. Okay, and it's easy to see that the core of a graph will be a core. Okay, and if the graph's the core, it's the core of itself. So it's not too unreasonable to be sloppy, but the point, you have to be a little bit careful with it. The words it's used with two slightly different meanings. You talk about the core of a graph, and you talk about whether a graph is a core. Now, I didn't come up with this terminology, so I don't feel obliged to defend it, but that's just what it is. And so the point to bear in mind is the two things are different. Now, as you get familiar with the stuff, you decide it becomes easy to ignore the difference. But when you're first learning, it can be confusing. So there are two different concepts. There's the core of a graph, which is the smaller subgraph to which you have a homomorphism to, and there's a graph which is a core where any endomorphism is an automorphism. Now, the simplest example of a core of a graph is take a bipolar graph with at least one edge. Now, I can probably help with it. So we have some bipolar graph. Now, the map that takes projection onto K2 is a homomorphism. And you can, in fact, it's an endomorphism of the bipolar graph to itself. Now, you can't map the bipolar graph, if the graph's got an edge, you can't map it. There's no homomorphism taking it onto K1. So this is the smallest you can do. And so you can say the graph is bipartite if only if its core is an edge. Now, there are many definitions of bipartite graphs, and this is probably the most awkward. Okay, so the core of a the core of a graphs bipartite if the core is an edge. Now, I want to talk a bit about cores. The issue is when we get to the quantum case, it turns out we don't yet know how to define an analog of core. But I want to add a few things just to explain why cores are interesting. First thing is, and this would be an easy exercise, I'm not going to assign it, that all cores of X are isomorphic. Okay, so that they're isomorphic as subgraphs. Now, since I haven't defined isomorphisms, you tightly complain, but we'll get to that. So the cores are all isomorphic. The second thing is that if the graph is vertex transitive, then any core of the graph is vertex transitive, and the size of number of vertices of the core divides number of vertices of the graph. So these aren't things we'll be working with, but my point is that there is some theory attached to cores, and there's some interesting things you can say. And I'll leave it at that. And here I'm just saying, well, if you have a homomorphism from X to Y, then that determines a partition of X. And so the set of things which map to a given vertex, I'll usually call a fiber or a pre-image. And the fibers of the homomorphism partition the graph into co-cliques. And so if you're interested, and so that any homomorphism determines the coloring, but we won't worry about that. Now we will need to consider homomorphisms into infinite graphs, and I just want to give one example. And so this is not just in quantum context of quantum things. It creeps into various places. So I'm giving you an example where there's the infinite graph I want to work with is, I'm going to call the orthogonality graph in D dimensions. There's vertices of the unit vectors in R to the D, and the edges, two vertices U and V are adjacent if they're orthogonal. So that's a perfectly reasonable definition of a graph. So your vertices of the unit sphere in R to the D, and they're adjacent if they're orthogonal. Nothing wrong with that. It's a definition of a graph. Now, a homomorphism from some usually finite graph into omega D is called an orthogonal representation of X. And this comes up in Lovaas's work and the related work on Shannon capacity, things like this. So these things arise independent of any physical applications. We'll see there are some eventually. So it's a natural question. So then you ask, when is there these homomorphisms exist? The first thing to notice is that if you're dealing with the omega D, then any orthonormal basis of R to the D gives you a clique of size D. And it's reasonably easy to show that you can't have a larger clique. So the maximum size of a clique of omega D is D. Okay, so that's nice because generally, if I just give you some big graph, it can be very hard to say what the size of the largest clique is. So this is an infinite graph with uncounted many vertices. In this case, the maximum size of clique is D. Okay. Now this graph does play a role in quantum physics, and I'll say more about later in the course. There's my comment about the orthonormal bases, and then there's an important. Well, this is a consequence of a theorem of Gleason's, and Gleason was basically proving a theorem about interpretations of quantum mechanics or quantum physics. That the one consequence that falls out of this is if D is at least 3, there's no clique in omega D that contains exactly one vertex from each D clique. Now let's just be concrete and think about R3 for a minute. We've got our sphere in R3. Now, and so we have 3 cliques coming from the orthonormal bases. Now, if I can 3-color the vertices of omega 3, then each color class must have exactly one vertex in each clique. If you have 2 vertices in a clique, they're adjacent. Okay, so what this result tells you is that the grammatic number of this infinite graph is greater than D. Okay, now the interesting thing is that this is following from something, as I said, involving interpretation of quantum mechanics, and I'll say more about that towards the end of the course. But from graph theory point of view, we have a nice concrete statement. This graph has got a clique of size D, but its grammatic number is at least D plus 1. Any questions?
I had a quick question. So, omega D, isn't this an infinite graph?
Yes.
Okay.
Yeah, I mean, that was the whole point. I said we're going to use homomorphism in infinite graphs.
Okay. Okay.
And this is the example. Okay, and what my point is that, well, as I said, Lovas was working with these orthogonal representations in his work on the Shannon capacity, no physics in sight. Okay, so so from a graph theorist point of view, in terms of coloring problems, it turns out to be reasonable to consider this sort of situation. Another example which will come up is if you take the unitary matrices, the D by D unitary matrices, you could define graphs on that, and there are questions of interest about homomorphisms from finite graphs into that, but I'll come back to that much later. But definitely so the point here is that the target graph is infinite. Generally, the problems we're looking at, the graph, we're looking for homomorphisms from some finite graph into an infinite graph. I don't think we have any cases where we're looking for homomorphisms from one infinite graph to another. I don't know any places where that happens. It could happen, I guess. Any other questions?
Isn't the theorem kind of trivial?
No.
It's like you have an infinite number of D cliques, and that's why you can't.
Well, first thing, it's false if D equals 2.
Right.
Okay. Because you're just looking at the circle. It's not trivial at all. It implies something called the Koch and Specker theorem, which professors, like people in quantum computing, are very fond of. And so it's not trivial at all.
But don't you have an infinite number of cliques?
Yes.
Of D cliques? So why?
Yes.
How could you? And if we know that D is the maximum size.
Well, the point is, if I have a coloring with 3 colors, then I've colored all the vertices of the graph, and so I've assigned a color to each vertex in each D clique. So if I 3-color my graph, then for each D clique, there's a color associated to the 3 vertices, to each of the vertices.
Okay.
Yeah. Yeah. Now, Gleason proved something a bit more general than this, and the proof of that is complicated, and I don't think I've seen it. I might have seen one physics proof book which gives a proof of it, but I don't think it does. In fact, no, the only proof I've really seen is the original proof by Gleason. And the physicists just wave their hand and say it's very complicated. But so, yeah. Any other questions?
Oh, and I guess I took this for granted. We're saying size is number of vertices, not number of edges.
I always say I can never keep track which is the size and which is the order.
Okay.
And so,
Here you mean
I'll be explicit. So in this case, where did I use size?
the
Yeah,
top
the
of the
size
page.
of the click is number of vertices.
Okay.
Yeah, so I probably tend to use size for number of vertices, but yeah, all I'm going to say is if you get confused about this, I'm not going to criticize you.
Okay. Thank
Okay.
you.
On the other hand, try and be explicit so we know what you're talking about. Okay.
Sure.
Yeah, because there is this size versus order, which I find very hard to keep track of. And so the problem is when I'm teaching a course to undergraduates, and you suddenly bring in size and order, and then for the rest of the course, people are getting size and order confused. They can't be helped because you learned them both at the same time, and there's no way of telling which is which by staring at the term. The other thing drives you up the wall is when people use maximum and maximal to mean different things. But we won't go there. Any other questions at this point? Okay, so I've already used the term isomorphism, and I guess I'm hoping you were familiar with it, so now I want to go into more detail. So an isomorphism between two graphs is a bijection from the vertex set of the first graph to the vertex set of the second graph, such that the if U and V are adjacent to X, then their image in Y is also adjacent. Okay, now this time I've been more careful and indicated where the adjacency is. So that's an isomorphism. Now, generally speaking, when we talk about most of the properties of graphs that we care about, like chromatic number or the girth, if two graphs are isomorphic, these parameters have the same value. Okay, but there are parameters which do depend on the graph and not just the isomorphism class. For example, the adjacency matrix. Okay, now I'll say more about that as we go on. But so the point is, in any case, an isomorphism from a X to Y is a bijection from vertex set of Y to vertex set of X to vertex set of Y, such that these conditions hold. When people start talking about unlabeled graphs, they normally mean isomorphism class. And so if what they're saying makes sense, then you can get the sense by translating unlabeled graph to isomorphism class. Now, okay, an automorphism of graph is an isomorphism graph to itself. And the isomorphisms are functions, and so you can compose them associatively. And so automorphisms are invertible functions, so you get a group, and that's set of automorphisms of a group, and that's noted by order of X. We can make it a bit less abstract. So an automorphism of the graph is a permutation of the vertices. It's a bijection of the vertex set to itself. And so you can view the automorphism group of the graph as a subgroup of the symmetric group. And in that case, you can say Ord X is a permutation group. Okay, so the automorphism group is a permutation group. It's a subgroup of the symmetric group on the vertices. Now, the equality here is saying, I mean, if the Ord X is equal to the symmetric group, then it's an exercise. I won't be assigning a proof that your graph must be the complete graph or empty graph. Might be worth adding here that, no, I don't want to. Just also, the automorphism of the graph is equal to all of its complement. Now, if there are any topology, they get confused because the X bar is likely to be some sort of closure. But in the context of graph theory, the X bar will normally just be the complement. So you throw away the edges there and put in the ones we're missing. And so a graph and its complement have the same automorphism group. They're equal. There's no isomorphism anywhere. And that can be useful occasionally. I don't want to do anything else. Yeah, now, so automorphisms of graphs are permutations, okay, with the property that if I is adjacent to J, then the image of I is adjacent to the image of J, and if I is not adjacent to J, then the image of I is not adjacent to the image of J. So that's an automorphism. Now, as traditional list pointing graph theory courses to give some graphs and ask people to work out the automorphism group, and there's not a whole lot of point in doing that, to my mind. If you do want to get the automorphism some fixed graph, then the easiest thing to do is to stuff it into Naughty or into Naughty and Sage and ask it what the group is. Well, it'll give you the order, which is generally all you want. Okay, so there's no real point. The problem is that by staring at the picture, it can be very difficult to see what the automorphism group is. Now, the standard example is the Pearson graph. Everybody said, okay. So there's the Pearson graph. Now, what is the order of the automorphism group of the Pearson graph? Now, you can see there's a five-fold rotation through 2 pi and 5, which leads to x invariant. That gives an automorphism of order 5, and so that gives us a subgroup of order 5. And you can also see that there's a symmetry about the vertical line there, so that gives you an element of order 2. And so if the order of the group is divisible by 2 and 5 is divisible by 10, what's next? Now, I would say that's all you can see from this drawing. Now, if you draw the graph by starting with a vertex and then going outwards on neighbors, you might decide there's an order of order 3, or maybe even and another, in fact, a subgroup of order 6. And so we're now up to 6 times 10. Okay, so the order was the group would have order of at least 60. In fact, the order was the group has order 120.
Sorry, what
Okay.
was that last transformation you were suggesting? The last
Rotating it, well, there's 6 vertices left out. If you draw things neatly, you'll see there's a rotation through 2 pi and 3. And again, there's a vertical symmetry of order 2. Now, you want to be careful that that symmetry of order 2 is not the same as the one that I'm talking about here. But what I'm claiming by filling with the sort of argument I've just given you, you can bring yourself to arguing that the order of the automorphism group is at least 60.
Right. Did we already count like sort of swapping the inner 5 points with the outer 5 points?
Well, that's not clear.
Okay.
I mean, it's a very good question. You have to first verify that is indeed an automorphism. And I think the way you described it, it won't be. The one point of this is that, in fact, if you have a drawing, then you can often see some automorphisms. But it's important to bear in mind that different drawings will show you different automorphisms. Okay, and so by that, so you can build up a collection. And so in many cases, you can actually build up enough and so maybe if I add in that one you just referred to, I get 120, and that is in fact the total. But in fact, now you've only done half the work at this point, because the second point is to show you have them all. Okay, now there's an example I'd like to use. Actually, I'm going to do it now. Is to take I said the Pearson graph, where you took the pairs, 2 subsets of a 5-set adjacent if disjoint. So that was the definition I did with the 0, 2, 1, 3, ... Now, from that definition, you can actually see that the symmetric group on 5 letters is giving you, or each element of the symmetric group on 5 letters gives you an automorphism. Because each element of the symmetric group on 5 letters permutes the elements of the 5 set and it permutes the pairs. So from this description, from this description, I could deduce that there are at least 120 automorphisms, the elements of the symmetric group on 5 letters. Now, I've got to be a little bit careful here, because the symmetric group on 5 letters, its elements are permutations on 5 symbols, but they're also permuting the 10 unordered pairs. And so, so that's a permutation of 10 things. So we have a permutation group on a set of 10 elements. And that permutation group is isomorphic as an abstract group to the symmetric group on 5 letters. And does anybody want any of that clarified? Okay, I'll trust you. I want to consider. Oh, no, it's wrong. I want to take the 3 subsets. I get 0 to 6. Now, notice in this case, there are 35 3 subsets, and so I could declare them adjacent if they meet in 2 elements, or 1 element, or no element. So no element would sort of be analog of that. Okay, but I'm taking 1. Okay. Now, again, the symmetric group on 7 letters permutes the set of 7 things, and so it permutes and maps 3 subsets. So the order group of this graph on 35 vertices contains a copy of the symmetric group on 7 letters of order 7 factorial. In fact, the order of the Olsen group is 8 factorial. Okay. Now, if I took the 3 subsets that met in 2 points, I'd be all right. I would get 7 factorial. And if I took the things that met in, that were adjacent if they're disjoint, I would again get 7 factorial. But if I take the things which meet in exactly 1 element, the order jumps up. So the moral simply is if you're dealing with automorphisms, then one needs to be careful. Okay. And as I said, you can usually find a good fraction of the automorphisms of the graph you're dealing with, but trying to decide whether you got all or not can be difficult. Now, it's a lot easier these days because Naughty works on graphs on tens of thousands of vertices as a rule. So you can get automorphism, size the automorphism group and the generators of the automorphism group without thinking too hard about it. Okay. But the other thing is that really by staring at a picture of the graph or drawing, you cannot in general work out what the automorphism group is. Okay. You can find some automorphisms and things like that, but that's asking you to compute the automorphism group of a drawing is in general not reasonable. Now, I was describing automorphisms as bijections and hence as permutations. Now, there's a second description in terms of matrices that we'll need. And so let's go back to one of the, there's half a dozen sort of basic facts in linear algebra that you need. And one of these is a linear map from a vector space V to itself is determined by its values on a basis. And in fact, a linear map from V to W is determined by its values on a basis, but I don't need that. So a linear map from vector space to itself is determined by its values on a basis. If I specify the values where the basis vectors go to, then I've determined the linear transformation. And so if we choose this, the standard basis for V is R to the N, or F to the N, and we use a standard basis, then the values of the linear mapping on those elements of standard basis determine the linear mapping. That's comment. So that's in some sense comment number 1. So to determine the linear mapping, I just have to specify its values on E1 through En. Now I want to think about the case where L maps E sub I to one of the EJs for each I. So it's permuting the elements of the basis. In this case, we say L is a permutation operator. Okay. And the matrix representing L relative to given basis is a permutation matrix. Now, none of this is a surprise. So a permutation matrix has got exactly 1, 1 in each row and in each column. So I'm not changing. So you've seen permutation matrices before. There's nothing new here, except I'm talking a bit about operators because I might need to think about automorphisms of Kronecker products later on, or you might need to. So we can represent each permutation of 1 through N by an N by N permutation matrix. And so if we have the automorphism group of a graph, we can represent each automorphism by a matrix. And it'll be a permutation matrix. Now, that's what this is saying. The only problem is when you write down the matrix, you may end up writing down the transpose of what you really needed. Now, if I was feeling nasty and I was running out of problems for you to do, I would ask you to write down, take a permutation pi, what is the matrix that represents pi? And there's a 50-50 chance whether you get pi, whether you get P whether you get the right matrix or its transpose. In the end, it doesn't really matter if you just ignore it and go on, and sort of consistent with what you do, you won't run into problems. But if you want an annoying problem to think about at some point, you want to work out the rule. Now, the other thing to notice, and I should have actually I didn't know reason to mention it earlier, actually I must. I'm writing my permutations and my group actions on the right, not on the left. Let me just go on a little bit. So I'll come back to that comment about permutation in a minute. If you have a permutation matrix corresponding to permutation pi, then pi is in order X, if and only if the permutation matrix commutes with A. Now, in linear algebra, if you're dealing with a matrix, the things that commute with it are nearly always important. And so the permutation matrices to commute with A give you the automorphisms. And often when I'm working with, in many cases, it's often convenient to just take that to be the definition of an automorphism and then not worry about the permutations. Okay, so we have, in a sense, I have two definitions. One is to say it's a bijection that preserves adjacency and non-adjacency. The other is to say there's a permutation matrix that commutes with the adjacency matrix. Now, depending on what you want to do, one of those definitions might be more useful than the other. But the point about definitions is you get to choose, and you should always choose the one that makes your life easiest. Well, you can't do that when I'm giving you assignment questions, but you get the idea most of the time. And so this is saying here, I sometimes would define order X to be the set of permutation matrices to commute with the adjacency matrix. And now I wanted to make a comment. So if, oops. If G is a permutation group, omega, and I is in omega, and G is in G, the image. Now, I would normally just write it as I followed by G. When Gordon and I were writing a book, we had a bit of an argument at this, and Gordon sort of agrees with me, but he felt this was going to be confusing, so we often write this exponentially. Okay, and so I will probably try and do that a lot of the time, except when it gets down into a subscript or a superscript, I would tend to flatten it. So my operations are on the right. The way to think of this is that the analyst or calculus, you're thinking of functions, and when you say I have a function f composed with a function g, you have f of g. Okay, that's fine. But with group theorists, you're thinking of these group elements as operations. And so if I write down a, b, I think of doing a first and then b. They're not functions, they're operators, so there might be reflections or rotations. And so it's natural for in group theory to think of them, to interpret A, B as first do A and then do B. Now, I think it's fair to say the general consensus is to do it the way I'm doing it, but it's not universal. And I'm pretty sure when I first started, I did the other convention, okay? So it doesn't matter too much. There are times when this does make your life a little easier. The problem is sometimes you want something to be an automorphism and you discover it's swapping the orders of the factors. And so it can affect things under those conditions. But the important thing to notice is when I write down a permutation, so if I apply the permutation 1, 2, 3, 4, 5 to some, to I, well, it comes up when you're multiplying permutations. Okay, so if I'm multiplying two permutations, I'm going to say, well, 1 goes to 2, and then 2 goes to 3, so 1's going to 3. Now 3 goes to 1, and then 1 goes to 2. And so then 2 goes to 3, and 3 goes to 1. So that's interesting. But so my point is I'm calculating from the left. Okay, so I apply this permutation to my I, and then I apply this, and then I apply that. Now, so that's what I'll be doing. That's the notation that's used in the algebraic graph theory text. If you it's probably not going to matter too much because we won't be doing explicit calculations. But just bear in mind that I'm right, and when I'm writing these things exponentially, and so in particular, so that if I write down GH, then I'm thinking of G and H operations, and I read that as saying do G and then do H. And so if I apply this to a vertex, I apply G to the vertex, then I apply H. Now, it probably won't cause a problem unless we're doing an explicit calculation. I'm not sure. But anyway, that's what it is. So just be warned. And that's a good point to stop. Any questions? So in the next lecture, I'll be continuing with, I'll be basically talking about orbits and orbitals. And if you've seen permutation groups before, then you'll certainly have seen the orbit stuff and the orbitals. It's reasonably simple. And then I'd be talking about generating functions in formal power series, and then I'd be talking about graph spectrum. And the other point I should make is I'm going to try and remember to put, when I have a draft of the next lecture, I'll put it on the web page, on my web page, and so that will generally contain a draft of the next lecture. Now, and so I won't. I'll just delete the old lecture and put in the new one, and the final lecture that I'll edit this a little bit and then submit it to fields, and so that's what the edited version of what I've just done will appear on the fields web page. Are there any questions about that? Now, I asked if anybody had a preference for times of office hours, but nobody said anything about office hours. I'm willing to hold them, but you have to tell me if you want them. And as I said, my first choice was going to be the hour after these lectures on Mondays and Wednesdays. But I mean, basically, if we can it should be possible to arrange, 10, 15-minute conversations other times without too much trouble.